수업이 이제 학기 끝나가서 어나운스먼트 몇 개만 하고 시작할게요. 그래서 대충 So this is the plan for the rest of the semester. I think we are approaching the end of semester really fast. So this Thursday, this coming Thursday is a due date, due date for the term project number 1, part 1. And unfortunately, I don't know it's unfortunate or fortunate, but unfortunately there will be no classes next week on Tuesday and Thursday because I'm traveling next week. But you know the labs will be held as usual. I mean on Thursday and Friday we're gonna have the last lab next week will be held as usual, and the 12th. The June 12th, we're gonna have the last lecture, which is course summary, and is followed by Q&A session on Thursday. So we want to fix the date for the final. Okay, let's do a quick poll. Our proposal is, why don't we have the final exam on Thursday, June 14th, in the evening, during the lab time. How is it? Any objection? Any? 괜찮아요? 6월 14일 저녁. Don't care. 그닥 개의치 않는 분위기? 너무 쿨하게. 네. 그게 좋은 옵션, 좋은 걸까요, 그게? 그런가? 그렇네. 좀 뭐 그럴 수도 있긴. 주말까지? 그 주 주말까지? 그거는 괜찮을 것 같아요. 어때? 그 주 주말까지 텀프레트 1 해도 되나? 텀프레트 2. 네. 그런가? 이렇게 하면 어떨까요? 그냥 목요일 날은 우리가 시험 보니까 검사를 못 하잖아요. 그죠? 그러면은 금요일 날 랩 시간에 검사를 받든지, 아니면은 뭐 토요일, 일요일 중에 하루 정도 추가로 뭐 검사하는 날 하루 정도. 그냥 그 정도? 근데 뭐 일요일 오후 아니면 뭐 토요일 오후 뭐 하여튼 그 이틀 중에 하루에 그냥 검사 받는 걸로. 근데 랩2는 옵션이에요. 이건 다 하셔야 되는 게 아니고, 진짜 나는 이 프로젝트를 너무 좋아해서 꼭 해야 되겠다, 그런 분들한테 보너스 점수를 조금 주기 위한 약간 그 정도의 옵셔널한 프로젝트라서 꼭 하셔야 되는 건 아니에요. 그렇게 하시면 돼요. 대략 그렇게 하면 어떨까요? 그냥 제 생각에는 아마 저희가 생각하기에는 모든 사람이 다 할까? 모든 사람이 다 할까요? 별로 많은 팀이 아닐 거라고 생각을 하긴 하는데, 뭐 그냥 반쯤 하려나 모르겠지만 하여튼 반치해야 되는 그런 건 아니니까 뭐 하실 분들은 뭐 작년에도 비슷했던 것 같아요. 작년에도 옵션으로 했고 올해도 옵션으로 해서 하실 분들은 금요일 또는 뭐 일요일 뭐 이틀. 네. 네. 아니요, 최적화 아니에요. 그러니까 지금 옵셔널 한 거는 저희 그 픽스 플로팅 포인트 맞는 걸 픽스 포인트로 바꿔서 하는. 그게 옵셔널 프로젝트. 그러니까 성능 최적화는 그러니까 저희가 지금 이제 아직 현재도 지금 어떻게 이거를 잘 디자인해야 되는지 좀 고민하고 있어서 서브젝트 체인지라는 일단 그걸 주고 말씀을 드리면은, 일단은 메인 그 옵셔널한 프로젝트는 지금 플로팅 포인트 연산으로 구현한 거를 픽스드 포인트 연산으로 바꿔가지고 연산을 처리하는 게 일단 옵셔널한 프로젝트고, 대신 성능 옵티미제이션은 옵셔널하게, 그러니까 그 프로젝트의 내용은 아니지만 한 탑 N등까지만 한 1, 2등 정도? 탑 1, 2등 정도 성능 제일 좋은 학생 한두 팀 정도만 조금 보너스를 줄까, 성능 면으로 보너스를 줄까 하고 있어요. 어드밴스한 그 우리 코더들을 좀 권장하기 위해서 일단은 기능적인 게 메인이고 그 중에서 이제 제일 성능이 좋은 팀 한두 팀 정도를 좀 저희가 보너스를 엑스트라 크레딧을 좀 줄까. 좀 가벼울 걸요? 왜냐면 이미 프로젝트 1이 있으면 사실은 거기서 일부 컴포넌트만 바꿔 끼면 되거든요. 그래서 사실은 그렇게 뭐 어렵지는 저희 생각으로는 아주 어렵지는 않을 거라고 생각하는데 뭐 그 저희 생각이고 여러분 또 받아들이는 입장에서는 다를 수도 있으니까 하여튼 그렇습니다. 그래서 뭐 옵셔널한 거니까 여러분들 뭐 하실 분들은 하시면 좋고 아니면 못 하시면 뭐 못해도 상관없고 기말고사로 잘 보시면 되죠. 뭐. 그렇습니다. 정확한 거는 목요일날 저희가 픽스해서 발표할게요. 또 좋은 질문인데 현재로서는 전범위를 고려하고 있는데 예, 후반전에 한 내용이 별로 없어서 후반전에 사실 한 내용이 별로 없어가지고 예, 그렇고 있지만 그것도 추후 정확하게 공지하겠습니다. 네, 조금 아직 내용이죠. 또 다른 질문. 네? 보너스 그게 옵션하는 게 그게 언바운드냐? 언바운드는 아니고요. 뭐 바운드는 당연히 있죠. 최대 몇 점까지 주는 건 있죠. 근데 최대 몇 점이냐는 저희가 좀 더 생각해보고 목요일 날 알려드릴게요. 뭐 마찬가지 아니에요? 그러니까 어쨌거나 그냥 여기 깐 점수에서 추가해서 주나 거기에다 더 추가해서 주는 건 어차피 본인이 받는 점수는 똑같은 거 아닌가? 그 왜 그게 차이가 있나요? 깐 차이가 있나? 네, 네. 설명해 주세요. 중간 트랜슬레이터가 필요해. 어. 이미 좋은 포인트네. 미안해, 내가 잘못했어. 그러니까 이미 그 텀 프로젝트 만점을 받은 사람도 더 추가로 받을 수 있냐 그걸 물어보시는 거죠? 네, 당연하죠. 네, 물론입니다. 랩을 이거 프로젝트 1을 만점 받으신 분도 그 추가로 받는 거죠. 뭐 레벨 프로젝트 1을 예를 들면 뭐 95점을 받았는데 거기서 뭐 더 100점까지만 차는 게 아니라 거기에다 플러스 그냥 주어진 한도 내에서 대신 그것도 이제 점수에 얼마까지 더 줄 건지는 이제 그 한도는 있죠. 예. 또 any other questions? 오케이. 자 일단 이렇게 하고 그러면 날짜는 저희 기말고사 날짜는 6월 14일 저녁에 보는 걸로 일단은 날짜를 정할게요. 7시부터 9시. 다른 얘기 없으면 7시부터 9시 시험 보는 걸로 하고요. 그리고 뭐 텀 프로젝트에 대한 거나 그다음에 기말고사의 나머지 디테일에 대한 거는 저희가 좀 아직 조금 사실은 아까 얘기한 대로 좀 정하지 못한 부분이 있어요. 그래서 그거는 좀 저희가 확정해서 빠른 시일 내에 공지하도록 하겠습니다. 됐죠? 오케이. 자, 다시 그럼 이제 수업으로 Let's move on. 자, 여기가 slide 49. So let's start from here. So last time we covered basic operations of two types of neural nets, MLP and convolutional neural nets, CNN. And I explained how these network works, and how we can train this network as well. Using the back propagation technique, we basically propagate the error to different weights, so such that we actually minimize the error, right? So that's what we did. So today we're gonna move on to like hardware designs for neural nets, because today, as I introduced, as I said in the introduction, many IT companies or IT giants, they actually make their own like hardware platforms, especially to accelerate AI workloads. So let's take a look at a few of them. One of the first one is Google TPU. I think I introduced this thing a little bit, in the beginning of the course. So Google actually built their own like a processor called Tensor Processing Unit, or TPU. So this is nothing but big like matrix multiplier. I mean, matrix multiply accelerator. So this actually shows the internal design. Like there's some like a block diagram, whatever it means. I mean, but it's basically this is a design called a systolic array. So it's very archaic, like old design parallel computer. The basic idea is we actually place this adder and multiplier in 2D array, and then the input data comes in one direction and weights coming in on the other direction, and these data actually flow. One matrix actually flow in this direction, the other matrix flows in this direction, and they actually make rendezvous at a certain point of time, at certain adder or multiplier, such that we can actually perform this matrix multiply in a very efficient manner. So this is the if you see, I don't know, it's very hard to read, but this is like a matrix multiply unit. That's what I call like a systolic array. So that's basically the heart of the design. And this is the main centerpiece of the design. And also, Microsoft also have its own platform called like Catapult. So Catapult is the FPGA based on FPGA, like what you're using for projects. They actually have a bunch of array of FPGAs, and they actually use like this like a multiple FPGAs to execute neural nets. So they actually built their Bing search engine on FPGA-based server. So FPGAs are used for both this indexing, like like a page rank, or basically we do indexing for the search, and also it is also used for the deep learning accelerator. So here they actually there's some like articles published in public domain revealing the secrets of their design a little bit. And as of today, I mean, the most widely used platform for deep learning is GPU. If you play games, I mean, you probably know a lot about the GPU design. But the GPU is used for both like training and inference. But this design, this is Volta. This is actually introduced about a year ago. So it's like a May 2017. So this is a year ago. Okay. So this one is actually claimed to be like a 2 to 4 times faster than Pascal GPU, which was the previous generation. And they actually compare. ResNet is one of the CNN. ResNet is convolutional neural nets, which is very popular for like image processing, like image recognition and so on. So ResNet. They actually claim that this P100 is previous generation and V100 is like a current generation, and they claim when you actually train this ResNet, it can reduce the training time by 2.4x for training, and also for inference, this ResNet can be faster than the previous generation by 3.7x. And then mainly due to the special processor core called Tensor Core. Because in Volta, in this generation, they actually integrate like a special processor core called Tensor Core, which is used for accelerating the AI workloads. So in Tensor Core, this is very much optimized for 4x4 fuse multiply add. Okay, what it does is it takes like 3 matrix as input. So a matrix 4x4 matrix. So this is A, this is B, and this is C, right? And what it does is it performs multiply and add. So it's basically a simple like vector. I mean, matrix to matrix multiply and add a constant, right? So that's what happens. And internal of Tensor Core,
But the interesting thing is they actually use floating point 16 format for inputs, FP16. So the floating point format you know is like FP32, which is the 32-bit floating point like a type. But actually they use they actually support 16-bit floating point. The reason why they actually use this like a reduced precision data type is that this convolutional neural net is this neural nets in general, they have a lot of redundancy. Okay, so a lot of redundancy means that even if you reduce the precision of data a little bit, it doesn't really affect the end-to-end accuracy. That's the observation. So they actually, they actually they apply what is called a quantization. So quantization is basically, they actually reduce. Let's say we originally have like a 32-bit number, but maybe we only use like 8-bit or 16-bit to represent the same number at a reduced precision, right? In that way, we can actually reduce the computational strengths because let's say you have like instead of having 32-bit floating points, now you actually have let's say 8-bit or 16-bit integers. Then actually now you can use like a much simpler integer adder instead of like a floating point adder or multiplier. So that actually reduces the computational strength on one hand. Also, it actually reduces the total amount of data or bytes, right? Because now single element, single piece of data now only takes like 16 bits instead of 2. So now you can actually reduce the size of on-chip buffer accordingly, right? So that's the source of improvement. Why this one is more efficient than the original FP32. So here, in this tensor core, they actually use two. This is, by the way, this is called mini float. So mini float is, if you remember, like the original like floating-point number format, we actually have 32 bits, and the MSB is a sign bit followed by exponent, followed by mantissa or fraction, right? And this is 1 bit, and this is 8-bit, this is 23-bit, right? That's the standard like a 32-bit floating point, right? But instead of doing this, now we only have like half of it in mini float. We actually have like, shortened like sign bit is the same, but like a shorter EXP and shorter like mantissa, and total number of bits like 16. So this is mini float or FP16. So by taking, let's say this one is input, and then this is weight. In the previous, like, the neural nets, input and weights. So input and weights are both represented using like a floating point 16. And then if you multiply it, then you actually do this like a, element-wise multiplication. Then, you end up getting 32-bit value, right? Because if you multiply two 16-bit values, then the result is actually 32-bit, right? Because if you multiply the range, actually become like larger. So if you actually multiply two 16-bit floating points, then you end up getting full precision products. So now the result is FP32, and then now you add constant, which may be either like FP16 or FP32 to the product, and finally your final result will be the FP like a 14.32. So that's what happens in the tensor core. So tensor core is nothing but big like FMA, like a fuse multiply adder, optimized for 4x4 kernel, 4x4 like a filter. So if you remember this picture, you actually have this is a convolution operation, and this one shows some animation because we actually have 3 input channels, maybe RGB, red, green, and blue, and we also have like the 2 output channels, and the output dimension is like a 2x2. So that's basically where this dimension comes from. And what it did was we first transformed this like a data into matrix, like 2-dimensional matrix, And also we also transform this filter into like a two-dimensional matrix. This one was called IM to call, image to column, right? Because we reduce the dimension of the data. So in that way, we can actually make this access pattern more sequential than before. So if you want to calculate the output value, we simply can do this like a calculate the product of these two vectors. Then we end up getting like a one output pixel value, like this, and so on. So that's what it did, like for calculating convolution. Yeah, that's what already explained. So what's like typical like a data size in this like a matrix multiplication? Because we converted this like a convolution operation, like a two-dimensional convolution operation, into matrix multiplication, right? Because now we only need to do this like a matrix multiply. Basically, we calculate the product of like row with column. Then actually we end up getting the value of one like output pixel like this, right? So this one is like input, and this one is a weight, like a kernel or weight. Right? So if you actually do basically calculate the product of this like a vector and this vector, then we actually end up getting like a value of one output pixel. And we repeat this process for the entire output pixels, then we are done. So let's think about some like a realistic case. AlexNet is one of the oldest like pioneering CNN convolutional neural nets. And let's think about the second convolution layer on AlexNet. So AlexNet, this one is the second layer. Second convolution layer. So this layer, this one actually has dimension of 55 by 55 by 48 times 4 bytes. That's the input size. Okay. So why is it 55 by 55? That's the decision. That's the design of the network. So that's what this Alex actually designed. Alex actually chose the parameter somehow. So in this layer, the size of image, this is the image size. So this 55 by 55 is the image size. So this is like a height and width, right? And 48 is basically the input channels, basically number of channels. And each data takes like 4 bytes because we are assuming like a FP32, a floating point value. So the original input size is like 580 kilobytes. But the problem is, if we actually transform this input into matrix, then it actually explodes. The size becomes really big. Why? Because now we actually have to multiply this input size with like a 5 by 5. Why is it so? So if you take a look at this slide, so here we have you probably remember this thing. Let's say this 4. If you remember this like 4. In this input matrix, the same piece of data appear 4 times, like a D4, here, right? Why is it so? Because when you actually compute an output, this like a D4, the one like element is used 4 times by 4 different output pixel, right? So in that case, this is kind of, in a sense, not very well optimized like I'm to call. But if you actually apply it, each element in the input is replicated by n times, where n is the size of the filter. Because as you actually slide this filter, this like a black box is a filter, right? Slide the filter, this like a D4 element, appears at one of these 4 positions as you slide it, right? So in the beginning, this one actually appears in the lower right corner, and if you actually move it to the like yellow box, then this D4 will appear in lower left corner. And if you actually further, slide it to the vertically, then this one appears in upper right corner, and if you move it further, then it's in upper left corner. So eventually, this like same element will appear n times, where n is the size of the filter, because it will actually appear in one of the n positions in the filter. Assuming this stride is 1. Stride is 1 means basically we slide this thing by 1 pixel every time. So if that happens, that's the reason why we multiply by 5 times 5. So input matrix size become 14 times 14.5 megabytes, which is a lot. It's like a 25x bloat in the expansion of the original data. So we do this to optimize performance at the cost of additional storage, additional memory overhead. Then the output size, is 26 by 27 by 128. So this one is, this one is the output pixel size, the output image size, and this is the output channel, number of output channels, and each output element takes 4 bytes. So output size is 387 kilobyte. The kernel size is, we assume a 5 by 5 filter. So each kernel filter actually has 5 by 5 in dimension, and we have 128 of them. So that's the number of output channels. And this 48 must be the same as this number of input channel, right? Because if you remember, we actually need one filter per each input channel, right? So because we assume 48 is the number of input channels, we actually need 48 filters make one set of filters, right? And then we actually have 128 of them. That actually makes the 128 output feature maps, output channels. So that's basically how we calculate this overhead. So if you actually draw it in the previous figure, the input is 14.5 megabyte, and the kernel size is 614 kilobyte, and the final output size, output feature map has a size of 387 kilobyte. 그 구석 쪽에 가면은 조금 이제 그런 경우가 있겠죠, 그죠? 구석 쪽에 가면은 이제 실제로 뭐냐면 이제 더 이상 데이터가 없어가지고 0인 부분도 있잖아요. 사실 그 말이 맞아요. 그 말이 맞고, 근데 이제 그 5x5 필터가 이제 그 마지막 바운더리를 넘어가가지고 이제 이쪽 하는 마지막 요 가생이 부분 빼고는 나머지는 다 저렇게 되겠죠. 그래서 사실 정확하게 엄밀하게 말하면 그 말이 맞아요. 그래서 정확하게 말하면 사실 이게 아니지만 대략적으로는 아마 이게 충분히 크다는 가정하에, 그 필터가 충분히 작다는 가정을 하면 아마 대략적으로는 맞는 숫자겠죠. 네. 맞습니다. So, any other questions? 자, 이렇게 매트릭스 사이즈가 정해지고, so, and the blocking is one of the most important optimization we apply for optimizing matrix multiply. So here is the idea. So, this typically on-chip, your processor only has some limited on-chip storage. Let's say VRAM, right? You only have a very small VRAM, right? So these data, input data, output data, and kernels, they cannot fit on-chip memory. Okay? Then what you can do? So let's say you only have a small VRAM. Let's say some tens of kilobytes or hundreds of kilobytes, very small size. But as you see, these input and output metrics are really big. Could be megabyte, right? And how you can do this computation efficiently? So that's the blocking technique. So blocking is basically divide and conquer. So we actually divide, calculate this matrix multiply using very smaller, basically we break this matrices into sub-matrices, and we compute this a multiply of these sub-matrices, and then we add them up, then we're gonna end up getting the final result. That's the idea of blocking. So let's think about very simple a two-way blocking here. So let's say this ABC is really big, so they never fit in on-chip memory. then what we can do is we actually make it like a small block. So let's say this is a block size. I draw this like this, like a yellow box is a block size, right? Then let's say we can actually fit this like a 3 blocks on chip. That's possible because we can make these blocks arbitrarily smaller, right? So let's say we have like a small block. So in this specific example, this one is a 1 block, and this one is 1 block, and this is 1 block. Input, weight, output. So we actually have 3 blocks, right? We assume that these 3 blocks actually fit in on-chip buffer, like VRAM or scratch pad memory or cache, something on-chip memory. Then what we can do? So here is the idea. So we actually copy these like 3 blocks into the chip first, on-chip first, from off-chip. Let's say our entire data is sitting in the DRAM, and then we just copy part of it, like 1 block worth of data into the chip, maybe FPGA or some like processor. And we actually read like this like shaded part, and also read this shaded part. And we compute matrix multiply of the two. Okay? So what's going to happen? 요거랑 요거랑 matrix multiply 하면 어떻게 될까요? So what happens if you have calculate matrix multiply? So in order to calculate like 1 pixel value at the output, we need to compute the product of this vector and this vector, right? But what happens, we actually do this matrix multiply of this thing versus to this thing. What happens? 이렇게 하면 어떻게 되죠? First of all, how many output elements we're going to compute by multiplying these two? Matrix multiplier 만약에 계산하면은 let's assume, let's say this is B, block size is B, and this is half of B, and this is also B, and this is B. Let's say the size length is B. Then how many output value we're going to compute by multiplying these two? 매트릭스 multiply 하면 B by B 매트릭스를 2개로 곱하면 그럼 B by B가 나오겠죠, right? So if you actually multiply these two, then we're going to actually have this B by B matrix as output. Okay. But still, then this one is actually complete, the result. This is only partial results, right? Why? 그러니까 요 점을 가지고 얘기해요. Let me take this point as an example. Then what we calculate here is that we only computed this vector, half vector. The inner product of this half vector and this half vector. So it's only like partial result, like a half result, right? So how we can make it complete? So we now, in the next round, we actually load the remaining half of the input and weight vector and perform matrix multiply and add the result to the original output matrix, right? Then we're going to end up getting the final correct result of the output. And we repeat this process for all the output in the matrix. That's blocking. Okay? So blocking is basically we actually divide matrix multiplication into small ones, smaller like a matrix multiply, and we could actually reuse this input data multiple times. Blocking actually targets scratch pad memory or shared memory or VRAM, depending on whether you use a GPU or a FPGA, depending on the platform. That's basically very widely used like a technique to accelerate this matrix multiply. So here, if you actually apply a blocking technique for tensor core, then the operation block size is 4 by 4. The basic operation size is 4 by 4, and we simply, you can think of it as like this one is 4, this is 4, and this is a unit. And single like a tensor core can process like a 4 by 4 matrix very, very efficiently. Then you can actually repeat this process for all these like a 4 by 4 blocks at the output. Then you're going to end up getting the final correct result. 네. 네. 왜요? 네. 네, 그럴 수 있죠. 네. 네. 그렇죠. 예. 그 말이 그러니까 사실은 이게 데이터를 근데 어차피 사실은 생각해 보면 예, 사실은 그 말이 맞고요. 데이터를 예를 들어서 뭐 읽어오는 오버헤드는 있죠. 읽어오는 오버헤드가 있지만 그럼에도 불구하고 항상 이게 만약에 없으면은 예를 들면 캐시로 치면 매번 캐시 미스가 나는 거거든요. 캐시 미스 나면 매번 오프칩에 가서 데이터를 읽어와야 되잖아요. 그러니까 그거에 있는 오버헤드에 비하면은 뭔가 블러킹에 의한 오버헤드가 있다고 하더라도 그게 훨씬 나은 거죠. 왜냐면 모든 데이터가 기본적으로 캐시 안에 있으니까. 그리고 또 더 그거를 또 옵티마이저를 더한 더블 버퍼링이라는 것도 하는데 더블 버퍼링은 뭐냐면은 한쪽에서 컴퓨테이션을 막 하는 동안에 다른 쪽에서는 그걸 백그라운드로 이제 다음 처리할 블록들을 읽어오는 이런 것들을 서로 오버랩해가지고 이쪽에 컴퓨트하는 거랑 이쪽에 데이터를 이쪽에서 읽어오는 이거랑 서로 오버랩해가지고 이게 레이턴시 하이딩하는 이제 그런 것도 있어요. 근데 뭐 어쨌거나 블러킹을 쓰는 것이 안 쓰는 것보다는 훨씬 아까 메모리 관련된 오버헤드가 왜냐면 더미넌트한 오버헤드이기 때문에 어떻게 보면은 그 조그만 그 온칩 이런 비램 여러분 쓰는 비램 같은 거 그런 조그만 버퍼를 어떻게 최대한 잘 써먹을 거냐 그거를 옵티마이즈 잘하는 것이 훨씬 중요해요. 그 데이터. 네. 네. 근데 사실 여기서 말하는 메모리는 우리가 얘기하는 D램 같은 메인 메모리가 아니고 그 프로세스 안에 있는 그 온칩 버퍼 메모리를 말하는 거거든요. 근데 그 메모리는 더더욱 비싸요. 그러니까 왜냐하면 이게 뭐 오프칩 사실 D램도 상당히 비싸지만 온칩 D램 같은 경우, 온칩 S램 같은 경우, 보통 S램인데 온칩 S램 같은 경우는 이제 그게 사실은 어떻게 보면 칩의 가격이 뭐랄까 그 실리콘의 크기에 슈퍼리니어하게 이게 증가하거든요. 그래서 이게 말하면 최대한 지금 작게 만드는 게 중요한 이슈여가지고 특히 더더욱 비싸요. 원빗당 코스트당 가격도 훨씬 비싸고 그래서 거의 예외 없이 써요. 이 기법은 거의 예외 없이 쓰고요. 예. 예. 그런 거죠. So if you applied if you use tensor core for blocking, basically as I said, tensor core is very well optimized for 4x4 matrix multiply plus add FMA fusion multiply add. So we actually use 4x4 as a unit to be processed by a single tensor core, and there are a bunch of tensor cores. They are running it in parallel. So they actually compute these like a 4x4 blocks in parallel using like a multiple like tensor cores. In that way, we can actually accelerate this the throughput of matrix multiplying. So here is like a spec. I mean, the Tesla V100 tensor core, which is a state of the art. And this tensor core is, as I said, hardware accelerator for 4x4 matrix multiplying and addition. So the point of this slide is that this one actually this generation tensor core actually provide 4x more compute power than the previous generations like a 14.32 cores, because in GPU the unit of processor is like a SM. SM is like a streaming multiprocessor. So if you stream multiprocessor is a kind of simple like a processor with bunch of like adders and multipliers. So in SM, this is like a spec sheet. So in like single SM, it actually provide 64 14.32 cores, meaning that you can actually process 64 14-point operations at the same time in parallel, right? Per SM. And because this one is like 14.32, this one is like twice as much capable as the 14.16. So if you multiply it by 2, then it's equivalent to like 128 like FP16 cores or FP16 units. But in tensor core, as I said, there are like 8 tensor cores per like a streaming multiprocessor by this streaming multiprocessor. So there are 8 tensor cores per SM, streaming multiprocessors. So and each tensor core has 64 multipliers plus adder. So this one is equivalent to 512 FP16 multipliers, 14.16 multipliers. And because we have 640 tensor cores on 80 SMs, so if you multiply it, then the throughput is 120 teraflops, which is a lot. It's a lot of flops. So this one is more 4x more compute power than FP32 cores. 그러니까 여기 아이디어는 뭐냐면은 쉽게 말하면은 그러니까 텐서 코어라는 FP16 플로팅 포인트 16비트 플로팅 포인트에 최적화된 코어가 따로 있고 그다음에 기존의 그냥 32비트 플로팅 포인트 오퍼레이션에 최적화되어 있는 FP32라는 코어가 따로 있는데 그러니까 이게 훨씬 트루풋이 높다는 거죠. 그러니까 그 텐서 코어를 쓰는 것이. 그러니까 텐서 코어가 왜냐하면 더 높은 플롭스라는 게 플로팅 포인트 오퍼레이션 per second의 약자죠. This is flops. Teraflops, right? Floating point operations per second. 그러니까 120 테라플롭스라는 얘기는 테라가 10의 12승이니까 10의 14승 정도죠. 10의 14승 플로팅 포인트 오퍼레이션 퍼 세컨드 할 수 있다는 거죠. 10의 14승 정도. 그죠? 1초에 10의 14승 플로팅 포인트 오퍼레이션 처리할 수 있으니까 엄청나게 많이 처리할 수 있는 거죠. 그죠? 사실은 this one is equivalent to like our like previous generations like a supercomputer. I mean, like 10 years ago, the supercomputer, with like bunch of multiple like a node actually has this amount of capability, but now this one has like only one chip. I mean, so it's very impressive scaling down of the form factor. So this one is equivalent to the supercomputer 10 years ago. Okay. So because in the previous generation we only had like a FP32 cores at floating point 32, so there is like a 4x more compute power than FP32. So we can simply assume that in ideal case, this generation's like a tensor core is like a 4x faster than the previous generation, but in actually it's actually more than 4x. Why is it so? Any guess? 답이 있구나. 그러니까 이전 제너레이션에는 예를 들면은 그 SM 한 개에 스트림 멀티플러스 한 개에 뭐 예를 들면 n 개의 플로팅 포인트 연산을 할 수 있는 그 연산기가 있었다고 하면 지금 새로운 텐서 코어에는 예를 들면 4배가 더 들어 있어요. 근데 실제로 성능을 매조해 보면 4배보다 더 많이 나온다는 거죠. 더 빠르게 속도가. 근데 좀 이상하죠? 왜냐하면 덧셈을 예를 들면 덧셈기가 한 개 있는 거랑 4개가 있으면은 맥시멈 아무리 빨리 해봤자 4배 이상 빨라질 수 없는 거 아니냐 이렇게 생각할 수 있죠. 그죠? 사실 그렇긴 한데 더 빨라지는 이유는 아까 얘기한 대로 메모리 관련 오버헤드 때문에 그렇죠. 메모리 예를 들면은 사실 100% 풀 만약에 이게 유틸라이제이션으로 100% 매 사이클마다 새로운 덧셈을 계산한다 그러면 4배 이상 빨라질 수 없겠죠. 그렇지만 실제로는 그 아까 얘기한 온칩의 그 버퍼에다 가져오는 이런 오버헤드들이 있어가지고 그 데이터의 사이즈를 반으로 줄여주니까 FP6 것이 FP32로 쓰는 거에 비해서 데이터 사이즈를 절반 이상으로 줄여주기 때문에 버퍼를 더 효율적으로 쓸 수 있는 거죠. 그래서 실제로는 in reality about like a 9x speed up for matrix multiplication. Of course, there's sacrifice for precision, right? Because in the previous generation, they only use like 32 points, but now, if you use tensor core, we actually use like a FP16 both input and weights. So there's like a little bit of a sacrifice for the precision of data, but in terms of number of operations, there's 9x speed up. Right? So any questions about what I covered so far? 요즘 GPU가 없어서 못 팔죠. 혹시 뭐 실제로 PC 조립해보시는 분들 해보시는 분들 있는지 모르겠지만 GPU가 요즘 그 딥러닝도 그렇고 그 다음에 저기 비트코인 마이닝 뭐 이런 것 때문에 이제 씨가 말라가지고 다 그냥 아주 그냥 그죠? 그래서 엔비디아 주가가 한 3배 올랐죠. 1년 동안 그동안 저것 때문에 얼마나 서스테이너블 할지는 모르겠으나 어쨌거나 지금 하여튼 상황은 그렇습니다. 굉장히 비싸죠, GPU가. Okay, so let's let's move on to the last part. I mean, our project. So what has it to do with our project? That's the question, right? So how we can apply this like a blocking technique for our simple MLP network. So that's the question. So here, what you're gonna do is very simple neural net, which can classify a number. So let's say you take 32 by 32 image of number as input. Then you're gonna have like some like hidden layers, and there's MLP. This is MLP, multi-layer perceptron. So we basically do some like a matrix vector multiply, and then eventually we're gonna end up getting the probability, right? The probability of the symbols, each symbol, or like 1 through 0. So here, in this specific example, we have like 1,024 inputs because if you multiply 32 by 32. Is like a 2 to the power 5 multiplied by 2 to the power 5, so 2 to the power 10, right? So it's 1,024 pixels. So let's say each pixel actually is an input to this like a net. And in the first hidden layer, we have 256 neurons. So that means this. If you think about this like a matrix multiply. So we take 1,024 inputs and perform like a matrix vector multiply to generate like a 256 outputs. Okay, that's what you do in this layer. So here is the the more concrete example. So here in each layer, M is like 1,024, N is 256 outputs. Perform M multiplications between M inputs and associated weights to give an output. So here this is the formula. So if you want to calculate the output 0, this is output 0, right? This is output neuron 0. If you want to calculate the output neuron 0, you actually have to calculate the sum of products for all of these like incoming edges, right? For second one, output 1, you have to calculate the sum of products for all of this thing from here and also here, like that. And you repeat the process until the end of the neuron in the layer, right? And then you can actually expand this like a vector. I mean, you can represent it as matrix vector multiply. So here there are a bunch of like weight parameters because we actually have how many weights are there. So number of weights are 1,024 columns multiplied by 256 rows. So we're gonna have like about like 256K elements. Right, 256K kilo elements. Then also we actually have input vector, which actually has 1,024. Then to calculate the first output, we compute the inner product of this thing and this thing. Then the output will be this one, output 0. And if you calculate the inner product of this one with this one, then you're gonna end up getting the second one, and so on. Right? So that's very simple, like MLP, one layer of MLP. So, as I said, this only is too small to fit all of this like a matrix and vector. Okay, so what we do is we apply tiling. So tiling is a savior. I mean, tiling actually saves us. So here, we divide large matrix into like smaller like sub matrices, and for each like a small matrix multiplication, input data is fetched once from main memory and is reused multiple times. Okay, so let's think about it. So what does it mean? So if in the previous example, these like a vector can be reused multiple times, right? To calculate output 0, we first calculate the inner product of this first row and the entire vector. Then that actually yield the output 0. For the second output, we also read like a second row in the matrix, but we actually use the same like a vector, right? So this one can be reused. Because this one actually will be the entire vector will be read like 256 times, right? But there's no reuse for this thing because this one is once it's used and it's just discarded. No longer we don't need them, right? So this is reused, but this is not reused. Then if you're a sensible engineer, engineer with common sense, then which data are you gonna put on chip? 어떤 데이터를 칩에다가 온칩에다가 갖다 놓고 계속 갖다 리유즈를 하는 게 뭐 리유즈 써버렸네. 뭐 이거를 올려놓는 게 낫겠죠? 이거를 온칩에다 갖다 놓고 계속 요거는 그냥 아웃풋에서 그냥 읽어와서 한번 읽고 버리고 한번 읽고 버리고. 캐시 여러분들이 아키텍처를 들었으면 캐시를 알잖아요. 캐시를 아신다면 일단 무조건 리유즈가 되는 애를 캐시에다 올려놔야지 이게 최대한 이게 캐시 에피션시가 좋은 거잖아요. 그죠? 그러면은 얘를 온칩에다가 갖다 놓고 얘네들은 그냥 한 번씩 그냥 쭉 스트림 읽는 것처럼 그냥 쭉 그냥 읽어서 그냥 들어오는 대로 계산하고 그냥 버리고 계산하고 버리고 캐시에다 올려놓을 필요도 없지 얘네들은 리유즈가 없으니까. 그죠? 그런 식으로 이제 디자인을 하는 것이죠. 그래서 so in this specific case, we actually reused inputs, right? So we actually fetch this input, part of input, worth of input, from main memory to on-chip buffer or VRAM, and then we actually compute like a multiple outputs using that same input. So here is a code example. So here, let's take a look at more complete, like concrete example. So here, how we apply blocking to like a matrix multiplication. 자, matrix multiply 보시면은 먼저 이 코드를 먼저 보세요. Let's take a look at this code. You understand this, right? matrix multiply 하는 코드 짜라고 하면 짤 줄 아시죠? 이렇게 짜면 되잖아요, 저렇게. 그지? 이 코드 이해는 되시죠? 3중 루프, 그지? triple loop. So, we actually for like a output ij, we actually have sweep this like a vector, right, on both column direction and row direction, and then we keep adding them, keep accumulating them along this like a row and vector. So basically we compute the inner product, right? So this is before blocking, before we apply blocking. And if we apply blocking, what happens here? So one notable difference is that in the previous like original version, the loop is incremented by 1 at every iteration, right? But in this case, what happens? I mean, this one's BS is the block size. And one notable difference is that the increment is now BS, like a block size, right? And then, what we do is, we start from here. Originally, these ij are both 0 and 0. So let's say, this is some like inj. I mean, it's not necessarily 0 and 0. Let's say this starting point is inj. Okay? Then what we compute is, we repeat computation for all the blocks, right? So if you want to compute like the value of this this block, then what you do is you basically first compute in first iteration of k, you compute the matrix multiply of these two blocks. In the second iteration of k, now you compute the matrix multiply of these two blocks, and so on. Right? So if you actually repeat this process over the variable k, then that's basically that's basically what we get as output. Okay? 자, 이렇게 이제 블러킹된 버전 이렇게 되는 거죠. 블러킹된 버전 이렇게 돼 있고. So this one is show like very tiny, like a concrete example, like with visualization. So in the previous, example case, we had to multiply. The vector size is 1024, and the output size is 256. And let's assume block size is 2, BS is 2. How this how this blocking works with matrix vector multiply. So here, before blocking, this is the version before blocking. And after blocking, this is BS, right? The block size. So now, the loop is incremented by 2, because now we actually compute like 2 by 2, block as a unit. So if you see here, now you actually compute this 2 output as a block. So just correct myself. So here, in this example, we compute like a 2 output as a block. And to compute this thing, in input matrix, this is a 2 by 2 matrix is the block, and 1 by 2 vector is the block. So if you actually, use this thing, so initially, j and I are both 0. Then, we first, in the beginning, we first compute, the partial sum, like a partial product for this thing with this like a matrix and this vector. So we actually compute, this vector and this vector, basically compute the partial product and update the value of output 0. And in the second iteration, in the second line, we compute the sum of product, inner product of this vector and this vector to compute the partial sum of this output 1, right? In the next iteration, we move it by 2. I mean, we move this like the window. I mean, this like matrix window by 2 vertically. Then, now in the next iteration, we compute the same way. Compute this thing with this thing to compute the output partial sum of this output 2, and also this one and this one to compute the partial sum of output 3. Okay. In the next iteration, we repeat this process until we reach the end of this row and end of this column. Then, by computing these two outputs, we compute these two outputs here, right? And then, actually, we move on to the next column, like this. Oh, sorry. This is this is true. So this one we multiply this one with this one to compute the another like partial sum of this output values, output vector, and we move on to compute the partial sum of this like two output values and add them to the output vector, and we repeat this process until the end of this column, and we move on to the next set of columns and so on. Repeat this process, and when we're done, we basically end up getting the final result. So that's basically how this blocking works in our setup. I mean, this is like a simple MLP network. Then how this thing actually works in our FPGA, in our like project. So here the MLP, the neural net is our application, and basically each layer is simple like a matrix vector multiplication, because we are assuming like there's only one layer. I mean, just simple one channel. So it's basically simple matrix vector multiplication. So so for example, like 256 by 1024 matrix by 1024 vector, then the next like output actually has 256 vectors. So we actually execute like this like a blocked version of the loop. What happens is, the ARM CPU, in your Zynq chip, the ARM CPU actually runs the main function, which actually calls your matrix vector multiply IP on the program logic, like PL. So for example, in one case, we calculate 8 by 8 like weight matrix in 8 entry input vector and multiply them as a unit. Basically, we compute like 8 output elements to get at one time. So let's say we basically take this 8. In the previous example, we actually had like a 2 by 2 weight matrix and 2 entry input like vector to compute like a 2 output at the same time, right? But in our like example, we increase the size of block to 8 by 8 weight matrix by 8 input vector to compute the partial sum for the 8 output elements at the same time. And VRAM is used for data transfer between hardware and software. So VRAM is our communication medium and buffer, launch buffer. So here, if you see this like block diagram, this is Zynq like PS, like this is CPU basically, ARM CPU, and we place our input data and the weights to this like a VRAM using like a memory mapped interface. And also, this like our IP, we also, trigger the beginning, the command, I mean, start computation using the command, maybe 5555 or something. I mean, some like, we give a command. Then this one, actually, this IP starts computing, this output for this 8 by 8 matrix with 8 like a vector, MB multiplier, and put the final result back to the VRAM like this. And then the software actually read this final outcome from VRAM back to the CPU. And we repeat this process for all the blocks in your matrix and vector. Okay. So that's what's happening here. In our project. So that's it. So I think this concludes a lecture, neural nets. So I think we can stop here. Any questions or comments?